Okay, so I wanted to show you here a way to traverse this graph, and it's really a graph, by the way, not a linked list. I noticed in your email that you referred to it as a linked list. A linked list is really something, you can see that, yeah, something like this, where we have only next from one node to the next, or we might have next and previous, or we might have a chain. But what you have here is a graph up in the corner here, and instead of looking at the whole data set, I'm just going to look at the first 3 rows of it. That's enough to require all the features that you need to solve a bigger problem. But again, it's an easier problem to look at. So I would work with this problem first, and then maybe I would mix up the numbers some to make sure that it solves this smaller problem, because I can debug it a lot easier than I can the bigger problem. Anyway, so but it is a graph, because when we go to form the connections, you see there's connections. There's 2 connections for each node, whereas a linked list would only have a next and a previous. So a linked list is actually a subset of a graph, or a type of graph. Anyway, let's go ahead and erase that. So I redrew, ignore that there, I redrew the graph down here. I drew it sideways. To be honest, I'm not quite sure why, but I guess that's just the way that I originally started looking at Dijkstra's. The thing that was really missing from your code, although all the code that you had was fine, the thing that was missing was you didn't have edge weights. So you had a graph that was a binary tree, but it didn't have any edge weights. Instead, you'd ascribe the weights to the nodes. And when you look at this drawing, it does look like the weights are on the nodes. But in my mind, it's really on the edges. So in redrawing it, right, so I rotated it 90 degrees to the left counterclockwise. A is my starting point, and this larger node here, that's going to be the ending point. And the reason I have A off separate is because I'm forced to follow this edge of 7, because I have to start on the first node. And by drawing it this way, I've given myself my first node, which has only one edge, where notice all the other nodes have 2 edges, until we get to the nodes that are on the base, which then are finally connected to the end node. Each of those only has 1 edge as well. So in terms of the C++, you could model this any number of ways, but to me, I guess the most ideal way would be the most flexible and most reusable way. I think what you could do is you could have, say, a struct. You see this okay? It looks a little blurry to me. Focus. Oh, that's better. Okay. Say I could have a struct edge, which could have in it a node pointer and a node pointer n or whatever, and then a weight. And then your node, then you could have a struct node, and it needs to have in it perhaps a vector of edge, edges. That allows me to have 1 or 2 or even many, so I could solve a lot of different graphs or different data sets. And then for each node, I also need to know if it's been visited. I wrote some of that up here, but I need to know if it's visited or not. which should start out as false. And I'm doing a little thing here. Sorry, I got a visitor right in the middle of my business here. And I need to know what the sum is. And the sum should start out as 0. So in this drawing that I'm going to traverse this to show you the algorithm. Let's see, what else do you need other than that? Yeah, that's all you need. So this simplifies it versus having a left and a right, and so on. Okay, and then to traverse this graph, I'm going to write some code, and I'm going to use a queue. So I'm going to make a queue of type node, and I'm going to initially push into that queue. I'm going to put the root, and then in my code I'm going to have a while loop that loops while I'm not empty, while not queue.empty. Whoa, is all this showing up on the screen? Sorry, I dropped the bottom of the node off, so go back to that for a second. So the node has a vector of edges in it, of which we will have either 1 or 2, and each edge has its own weight associated with it, and then each node has a visited, which starts out as false, and a sum. And the sum for each node is going to be represented by this empty circle. I'm going to change that sum, but they're all, the empty means 0 for right now. And visited is false. If I cross a node out with an X, that means it's visited. So that's how we'll be able to track that. In the end, the answer will be the sum in this end node. So we have to keep track of which node that is. So the goal is that we're not really just going to traverse it, but we're going to go through all the different pathways using this queue technique. And then the answer will be sitting right there. Okay, so while the queue is not empty, what I do is I pop the first thing off of the queue. So I pop queue into my node, and then so that's going to be here, because I started from, which I labeled as A, but that's really the root. So I look at A, and then I look at all of A's edges. I follow each edge, and I look at the sum of the node that I get when I follow that. And right now the sum is 0. There's nothing written there. 0 is less than 7, so I replace the 0 with a 7. Now, are there any more edges on that root? There are not, so I'm done visiting that. But I do take the node that was followed by the edge and I push it. So I follow all the edges and I push all the nodes I visit. So even though this is now dumped off the queue, this has been added into the queue. So after this while loop loops, now that 7 node is in the queue. So I pop it, I look at it, and I follow each of its edges. So when I follow up along the 8, the sum to get to there is 7, the sum I currently have, plus 8, which gives me 15. That's more than the 0, so I replace the 0 there with a 15. I push this into the queue. I follow the 3. 7 plus 3 is 10. That's more than 0, so I put the 10 in there. There's no more edges, so I mark that visited. But these two are in the queue now, so I have to go 2 more rounds of this. When I pop this one with the 15, when I follow up, 15 plus 0 is 15. That's more than 0. I put the 15 in there. And then this goes into the queue. I follow the 15 plus 1. 15 plus 1 is 16. That's more than 0, so I put a 16 in there. And that's all the edges, so I mark that visited. The next thing in the queue is actually going to be the 10, because I put these in after the 10 was already in there. So 10 plus 1 is only 11. That's less than 16. I'm trying to get the biggest number in each of these sums. So I don't replace the 16 in this case, because 10 plus 1 would only be 11. So I followed that edge. This is already in the queue, so I don't have to add it in there. It's okay if I did add it in there. When I come to it, it'll already be visited, so I won't process it a second time. Anyway, so now I continue with the 10. 10 plus 8 is 18. I put the 18 there because that's more than 0. I mark that visited. Okay. And now all three of these are in the queue. Alright, so the earliest thing in the queue is the 15. 15 plus 0 is 15. That's more than the 0 that's in there. I put the 15 in. I mark that visited. Down to the 16. 16 plus 0 is more than 15. So here's where I erase the 15 and I put a 16. That's all for that node. I mark that visited. And then finally down here, 18 plus 0 is still 18. That's more than 16. So I erase the 16. I have the 18 now in here and I mark that visited. And that's it. I would have pushed this onto the queue, and so I would process it in the last time, but it has no outgoing edges. And so in the end I would mark it visited. There would be nothing left in the queue, and that puts you down here in the code, at which point you simply look at the sum in the end node, which you have to have kept a reference to, and that's 18, which is the greatest sum, hopefully, that you can get by following the 7, the 3, and the 8. Yep, okay. I hope that helps. Anyway, that's just basic Dijkstra's. You don't have to have this structure. You could do it with the weights in the nodes. You just have to follow the edges. And you have to keep track of, you can still do that here. You don't actually have to have this part either. You could just add 7 onto the end and skip that part. But you do kind of need the nodes. You need this end structure so you have an actual end. That's one of the things that kind of a trick that was missing from the instructions, or they were leaving for you to figure out, is what do you do with the fact that there's so many endpoints? There's not really. You just have to build a fake endpoint onto there. I hope that all came across. Talk to you later.